minerals or metals or chemicals which are in the particulate form, and their evolution with respect to time as a function of various process variables. Okay, and different applications. It could be, let's say, for example, steel industry, granulation, pelletization, or coagulation and flocculation, which is important for water treatment industry, or nanoparticle synthesis, crystallization, etc. Basically, if you take any particulate system, you have a feed, and then they go through various processes. Particles get what usually we call birth. Basically, when you say synthesized particles or crystallized particles from solution, okay, or they may their size may get reduced due to, say, for example, breakage, or maybe say dissolution. Okay, they may grow big in size due to agglomeration. Okay, and then of course these are all physical processes, but there are also chemical processes which I am going to talk a bit later, where they interact with fluids. It could be a liquid or it could be a gas, and that is what I am going to cover today. With some of the examples where I have worked on. For example, most of these reactors could be classified under the traditional chemical engineering reactors, like, say, for example, packed bed reactors, where you have a bed of particles through which a fluid flows. Okay, and then rotary drum reactors. Generally, see, many of these processes also are at quite high temperatures. Generally, let's say something like 1000 degrees centigrade to as high as 2000 degrees centigrade. I will show you some of the examples later on. It could be moving bed reactors, wherein the particles will be moving from either bottom to top or top to bottom, and then gases or fluids may move in the opposite direction or in the co-direction. Okay, and then of course are also flame reactors. Okay. Just if you look at, I don't know how many have the exposure to actually working in industrial plants, but if you take any plant engineer, the basic objective of any of these plant engineers is to monitor how things are happening, and then of course optimize the production to maximize the tonnage or things like that, and of course ensure that the product is within certain quality limits, and of course energy consumption within certain limits and things like that. Obviously, there are a lot of complexities involved. One of the major complexities is, in addition to operating conditions, the quality of raw materials itself, especially when you are dealing with particulate matter. Unlike let's say fluids, the particles are highly heterogeneous in nature. Why is that? They are heterogeneous in nature, and also depending on the source, their nature changes. When I say nature, it is both physical as well as chemical. So their chemical composition changes from location to location, even within the same location. If you take any sample within this room itself, you might find that sample there will have a different physical properties and chemical properties as compared to a sample there. Unlike, say, for example, although in principle the air inside the room may have much more uniformity. So the particles are a lot more heterogeneous in nature, and their properties are functions of size. So that is another major problem, and they are highly distributed. So that means if you take any not only synthetic material but also naturally occurring materials, they have a wide size distribution. I will show you some of them later on. They may start from as small as let's say micrometer particles to millimeters and even bigger. And as you would all appreciate, most of these processes are dynamic in nature, although we do both steady state as well as unsteady state simulations and how approximate certain times, but inherently they are dynamic in nature, and the number of variables is quite large. So since, as I said, because the properties are distributed in size, it gets complicated, multiplied based on the number of size classes that one could actually describe. So if you assume that if fluid is uniform, you can assign same temperature, same chemical composition, same pressure to the whole atmosphere at the same one value. But on the other hand, if you have a mass of material, depending on the size, you will have different chemical composition, different properties, etc. So this, for example, a rotary kiln in a sponge iron plant. So this is, for example, at Tata Sponge Iron somewhere close to Jamshedpur. Okay. This is used basically to produce sponge iron, or more commonly known as direct reduced iron. What happens is that, and these are fairly long, very big, huge. So for example, this particular kiln is more than some 70-80 meters in length and about 4 or 5 meters in diameter. you have the iron ore coming in through here, it is reduced with coal, and air is used for combusting this coal, both along the axis as well as from the discharge end. And then due to reduction, I am going to show you some of the reactions that happen here. So here, so the materials are all in particulate form. So each of them have their own size distribution, and through a lot of laboratory scale experiments and trial and error, you find out what is the correct size distribution for this ore, what is the correct size distribution for coal, similarly for dolomite. And then based on that, and then based on the reaction kinetics, then you decide what should be the air that you have to use for this at this end as well as along the axis. One of the problems here is that many things cannot be measured online. Whatever is measured online also sometimes gets what I would say spoiled with respect to time, because as I said, a lot of unwanted material also comes here, especially with naturally occurring materials. For example, if you take, let's say, iron ore, the purity may be, let's say, about total iron will be about 90%, but the remaining 10% is actually what is usually called gangue, which is, let's say, alumina, silica, magnesium oxide, zinc oxide, things of that nature. Similarly, coal. So coal, I don't know how many of you know, coal will have fixed carbon, then volatile matter, then of course moisture. Moisture is another important parameter in all these things, because all of them absorb moisture, and then their properties change. Moisture keeps changing with respect to season. So how do you actually operate this kiln in different seasons, actually with respect to time as well as material properties changes. Then even the quality also you cannot get measured online. You have to actually take these samples, send them to the lab, and then you will get the analysis depending on how fast you can do the analysis. Some of these properties you may get, let's say, within an hour, whereas some of the properties will come almost like 8 hours later. Now, if the property does not match with your specifications that you have actually promised to your end customer, then all the product that you have actually produced is not really of use, and then you may have to throw it out or maybe recycle or do things like that. So this is some I have taken from some of this website. This is how it looks like. As I said, most of these are all actually involve combustion. They are at high temperature, so you will be using either coal or coke or some gas for combustion. So temperature varies from this end to this end, velocities change, pressures change, and obviously, of course, chemical composition and things like that. Other reactor, as I said, is a moving bed reactor. Okay, so that is the rotary drum reactor. So here, as I said, this is, for example, for another process where pellets are produced. Your pellets are charged from top to bottom, and then air is sent from bottom to top. There are a lot of things that happen. There will be drying, then cold devolatilization, oxidation, different reactions. Okay. Similar reactors are used, for example, say to produce quicklime from limestone. For example. So this is, for example, used in steel plants, but similar reactors are used in heavy chemicals plants, where, say, for example, soda ash is produced. Okay. One of the most commonly very popular used reactor that is used is blast furnace, which is even more complex. Okay, so what happens is, unfortunately, I didn't get a better picture, but I thought this was more colorful. I took this one. Almost similar thing happens. This is like, say, moving bed reactor, are traditionally called as vertical shaft furnace or vertical shaft kiln. That's what happens at the top of the kiln. But as it comes down, say from the bottom, you are pumping in air through blowers. Okay, and then pulverized coal is also injected from the bottom. The temperatures here can be as high as 2000 degrees centigrade. And as the hot air goes in along with carbon monoxide, etc., hydrogen, things like that, the iron ore melts. Okay, and then there will be you have multiple phases. You have gas phase going up, you have solids coming down, and then this melts keeps dripping down. Okay, and then of course there is moisture. So the modeling of such reactors is quite a complex task, and as far as I know, there are not many models which will describe everything that happens here. In fact, there is always the other extreme of people taking data and then try to do data-based modeling or even artificial intelligence modeling, etc. But there is always a trade-off. How much you can actually theorize things and then try to make it work, and at the same time, how much the data that you are measuring can actually represent what is going on inside. So I will show you where we have taken for one of those such reactors a hybrid approach. Then there are these fluid bed reactors. So one of these examples, say for example, this is a fluid catalytic cracking unit, which is used in a refinery to produce all these petroleum products, the petrol, CNG, etc., etc. This is another, this is a reactor regenerator combination. Okay. This is, for example, a fluidized bed reactor where the particles get fluidized. This say, for example, this is to produce silicon, which is used in solar cells. Okay. All of these cases actually are, as I said, examples of where both particle flow as well as fluid flow have a very strong influence on the productivity, quality, energy efficiency of these furnaces. This is another reactor. As I said, this is essentially a packed bed reactor. So you have these wet granules or pellets which are charged in a some kind of rectangular reactor. Okay, this will be something like say 200, 300 meters long. Okay, the width could be about 4 or 5 meters, sometimes even 8 meters, and the height could be about a meter. A rectangular reactor, where the reactors, so these wet granules which contain, let's say, depending on that industry, it could be in the case of iron ore, it could be hematite. In the case of alumina industry, it could be Al2O3. In the case of zinc, it may be some of those zinc mineral. Okay, so they contain this solid fuel, for example, carbon, some carbon source, coke or something like that. The bed gets ignited, and then the gas is sucked from top to bottom through blowers here, and then this red line here is the temperature, what they call heat front or heat wave, where the temperatures can rise as much as 1500 degrees centigrade. As the reactor moves from left to right, this heat front keeps moving from top to bottom. So all these wet granules, they get centered, and finally when it reaches the bottom, that means you have the complete reaction gets done. So the product gets discharged. This is in fact one of the most commonly used equipment you will see in any integrated steel plant. So I am going to talk about, so these are all various examples of where particles are reacted with gases to produce some useful products, either in steel plant or a chemical plant or things like that. So these are the examples. I am going to cover one of those case studies similar to this, which is known as induration of pellets. In fact, this is also a very common unit operation on any steel plant. Okay. Pelletization is nothing but making hard granules from ground enriched iron ore. Okay. It consists of what is known as boiling, essentially making of, take very fine powders, use some binder like moisture or lime, and produce what are known as pellets, and then heat induration is nothing but a heat treatment step. I will show you a little later. Finally, there are various physicochemical phenomena that happen. The important thing is that the product from this particular operation is actually used as a feed to the, I was showing you the blast furnace. So the productivity, energy efficiency, and quality of hot metal or liquid iron that is produced in a steel plant depends very critically on this pelletization plant. So we have been working on this to simulate this whole pelletization plant itself. So you have a boiling model, which is, as I said, these particles undergo various physical processes, for example. So this boiling is nothing but an agglomeration process, which is described using what is traditionally known as population balance models. There are nothing but integral differential equations. So you have to, there are no analytical solutions exist. Basically, there will be agglomeration as well as fragmentation or breakage, depending on the type of equipment that is used to undertake this process. Okay. Then another critical operation is this moving strand, which is, as I said, it will look somewhat like this. Similar to what I have described a little earlier. You have these wet pellets, they are charged as a bed of particles here, they move from this end to this end, and then the final product is discharged here. Various physicochemical phenomena take place here. For example, these wet pellets here, they contain moisture as much as, let's say sometimes as 10%. So you have to dry out that moisture before they can be sintered. Okay. So what you do, what is done here is that some of these hot gases which are produced in the, so essentially this is like another rectangular furnace. As I said, it will be about more than 200 meters length. This is the furnace here where you have burners on either side of the furnace producing hot gases, which will then are sucked from top to bottom to use this for drying. So some of these hot gases are used to dry out this moisture. So but what happens is that the bed is so high that it can only dry out some moisture from some part of the bed. So remaining part still remains wet. So what happens, what you do is that you take some other section and then recycle it, so that whatever moisture that is in the top portion of the bed is driven out. So before they actually these pellets come to this zone, what is known as preheating, so most of the moisture should get driven out. Otherwise, what will happen is that whatever combustion or calcination, any of these reactions that are supposed to take place, they will get delayed. and ultimately the production will come down, because the time taken for all the reactions will go up. Then combustion will happen, as I said, carbon will react with oxygen to produce carbon dioxide and things like that. Then there will be calcination, because they add some what are known as fluxes, limestone or magnetic MgCO3 or things of that nature. So there will be some endothermic reaction, there is an exothermic reaction, there is an endothermic reaction. Then there will be, because the temperatures go very high, so there will be partial melting. The entire material does not get melted, but partially there will be melting. And then before the complete material gets melted, then there will be cooling through cooling air. So there will be solidification, and then finally, because this is a very hot product, then some of the moisture that is present in the ambient air itself gets condensed here. So as you will see, you have solids moving from one side to the other. You have the gas phase, and then you have a third phase in the case of, let's say, partial melting. Okay. So this is a very highly coupled problem, as you could see. So there are things that are happening in the solid phase, there are things that are happening in the liquid phase. What one has to see is that how the fluid is flowing through this bed of particles. Okay. Fluid influences what is happening inside this particulate bed, but at the same time what is happening inside the particulate bed also affects the fluid flow and its properties in terms of temperature, composition, pressures, etc. So there, as I said, I have already mentioned, one of the major problems is that raw material characteristics, both in terms of chemical composition, size distribution and things like that. Many of these things, as I said, here these keeps on moving continuously, so you cannot really measure anything on the bed. So you can only measure what is the temperatures in the furnace here, and what are the temperatures and pressures at the bottom, known as wind boxes here. So, but the production, actual productivity, energy efficiency and product quality depend quite strongly on what is going on inside here. So that is another major problem with this particular process. Okay. So what we have done is, we make measurements, of course, whatever is possible on the plant, but at the same time you can conduct laboratory scale tests to find out what is going on inside in terms of temperatures and things like that, and use that to test these models with whatever extra data that one could get. Okay. The other problem, as I said, is that in addition to what is not known inside this furnace, the quality comes only every few hours and things like that. So what we have thought is that instead of leaving it as a complete, depending completely on laboratory analysis, use the model to predict some of this, what is going on inside, and also supplement this with the data that is being measured both in the lab as well as in the plant, and build a model for quality, which can then act as a soft sensor in a real time. Then use it for, so then you can actually have a model that will combine these two, the physicochemical phenomena model based on iteration, and then the quality model. Then you use to optimize the production, or say control production or quality and things like that. So I will go into more details of one of these ones subsequently. So this particular model is essentially a fundamental model. As I said, this is a fundamental model, whereas this is some kind of hybrid model. You take into account basic phenomena that happen, heat transfer, mass transfer, to take care of all the phenomena that I was talking about, melting, condensation, combustion and things like that. Take into account whatever the input properties of these materials, all the flow rates, pressures, etc., and also the actual bed, how fast it is moving, what is the height of this reactor, what is the length, etc., and then predict all this, what is going on internally. Okay. So again here, as you will see, there are various heat sources as well as heat sinks. So you actually take into account what is the heat that is getting generated, or exothermic reaction from combustion of coke. Okay. Then some of this latent heat that gets generated during melting, and that some of that gets used during solidification. Okay. Similarly, some of these endothermic reactions. Okay. So you take these into account and then formulate the energy balance. Okay. Similarly, you have to take into account what is going on in the mass balance. Okay. You have to take into account what are the various materials that are, these are all also multi-component systems. Okay. You have an air, but then you have to take care of oxygen, carbon dioxide, hydrogen, nitrogen, etc. Similarly, what is going on with the raw materials, what is happening to limestone, how much of it is remaining in solid phase, how much it is actually going into the gas phase in the form of carbon dioxide or water vapor, or maybe whatever is the unreacted oxygen and things like that. The other thing is another process, like I was mentioning, the condensation. What happens, as I said, especially you have when it comes down at the bottom of the bed, some of this material moisture that is present in the air gets condensed on the bed. So you have to take into account how this condensation is happening, where it is happening. Is it happening inside the particle or is it happening inside the bed? So you have to actually take into account, because that will change the flow characteristics. It will change the pressure drop across the bed. So you take into account how much is this actually going from solid phase to the vapor phase and then vapor phase to the solid phase. So if you look at the overall bed, you have some reaction zone, which I was showing you in terms of how is that temperature front. You will have some dried zone, so there may be some moist zone and then centered zone. So this will change from one end of the machine to the other end as the process keep going on. Okay, as I said, this will also, the pellets look somewhat like this. For example, some of those where granulation takes place, you have a core, what is known as nuclei, which is covered with a layer of these smaller particles. On the other hand, in the case of pellets, you may have multi-component system where you have particles of different sizes, different compositions. They may be not like a very nice structure, layered structure like this, but they are all distributed like this. So depending on the structure of this, some of this melting takes place. Of course, some melting may happen somewhere here. Sometimes depending on this, it may happen here. Secondly, then, as I said, various reactions that take place. It may, in addition to combustion and things like that, there may be parallel reactions as well as series reactions. For example, if you take, say, for example, hematite to final iron oxide, so then it may react with carbon monoxide and get this product. Parallel, so these two are parallel reactions. Whereas compared to this is a series reaction from this to this magnetite to eustatite to iron. Okay. Parallelly, there will be carbon gasification reactions. So these are all solid phase reactions. So these are also solid phase reactions that are happening in the coal. Okay. So then, and also you will have the gas phase reactions. Okay. So you have to actually couple all of them in addition to the flow and the other heat transfer phenomena that I was talking about. Okay. Traditionally, you do, of course, as far as possible, shrinking core model, but sometimes it works, sometimes it doesn't work. So then you have to actually modify this. How this actually, you start with a fresh particle, how the reaction front is moving inside. Is generally modeled using shrinking core, but depending on the nature of the material and nature of these pellets, then you may have to modify it to actually represent the kinetics of the reactions. Okay. So once you do all of this, taking into account all these things, then you write of course, this is now anyone familiar with numerical methods will know. Then you write the balance equations around this. For example, I am just showing you the solid phase, and then gas may move from top to bottom or bottom to top, and then write equations like this. You write energy balance equations for both the gas phase, solid phase, then pressure. This is one of the important things, because how this pressure drop changes will have very strong influence on not only this. Of course, these two, these are all coupled, as I said. And then what is on the right hand side depends on what kind of reaction that take place, what kind of heat transfer phenomena that take place. Okay, physicochemical phase change takes place. So all of them you have to actually incorporate. So each of these, for example, this is a combustion rate of combustion. So this is, for example, the rate of drying or condensation. This is, for example, rate of calcination, so the rate of melting. So depending on what kind of phenomena that take place, you have to actually incorporate. So each of these is again a complicated expression as a function of particle size distribution, gas composition, and things of that nature. Then you have to, of course, write down, depending on how much detail you want to get into, you write down individual balance equations for let's say solid phase components, let's say for example gas phase compositions, oxygen, say for example, or carbon dioxide, calcium carbonate, carbon, and things like that. So depending on what is of interest, then you write the equations, and then the right hand side changes depending on what phenomena that take place. Okay, and then you solve all of them together, because then these are all, as I said, coupled problem. So here we use, as I said, bed is moving from left to right, and then gas are moving either from top to bottom or bottom to top. So then you discard this whole thing into computational elements, and then solve this using what is known as alternate direction method. So you at each time step, so you solve from top to bottom and ensure that whatever is predicted in terms of the pressure drop. So you have to ensure that the predictions with respect to the pressure drop or the temperatures as well as the flow rates all converge at the same time. So you have to actually do essentially it is basically solving mass conservation, you have momentum conservation as well as energy conservation. but solved simultaneously for this system. Since the number of, because of the size of this reactor as well as the number of elements is very huge, you cannot really solve them simultaneously, then you actually do in a loop manner, interlinked manner. So you first solve for the conservation of momentum, so you ensure that all the pressure drop etc. is all fine, then you solve for the energy balance, then you finally solve for the mass balance. But when you do this in 3 loops, you ensure that at the end of all the 3 loops, then all the quantities are conserved. Okay. Then I mean, that is all what I talked about is the actual modeling part. And then now taking it to that real time simulation, then you put this in as a whatever I have described is all this process model. Then you take data from the what is let us say distributed control system, any source of data, laboratory information system, wherever you are getting this analysis through what is known as OPC gateway to a real time database server. So you access the data from here. Use this model to predict all these internal conditions of the bed, like say for example temperature profiles, moisture profiles, coke profiles. Use this information as well as the data and then predict quality parameters like this, some of these quality parameters which are relevant for this particular application. Then you do optimization depending on what you want. If it could be a single object to optimization or multi-object to optimization depending on what you are trying to optimize, and then or maybe you want to even control. So now you have, in addition to whatever you are measuring, the model acts as a soft sensor for both for the internal condition of the furnace as well as the quality. Then you try optimize and then download the set points. Okay. So another important thing is that anytime you go and try to show that okay, you have a model for a particular process, you have to make sure that it actually shows to the plant engineers that it works. And then there is no better way to do it than actually doing it on their own system. So you have to ensure that, let's say for example, these are the temperature profile below the bed. Like, see, there are measurements here, as I said. Okay, only all the pressures and temperatures are measured here. So the model is used to predict these things real time, and then test whether it is predicting correctly or not. Because only when they see that there is a good, fairly good agreement between the prediction as well as the actual measurement, then they will be acceptable. Otherwise, then acceptance will be very, I mean, they may not even accept it. So if it is not working fine, then you have to actually retune it or customize it or modifying say some of these heat transfer coefficients or maybe reaction rate constant, things like that. Ensure that this agreement is good, and then you use this model to predict things. For example, as I said, you have the complete bed temperature profile. So now you can put sensors at different any location you are interested, and then track it. For example, you want to see moisture, for example. Okay, how moisture is changing with respect to time along the length of the bed at different locations. Because this is, as I said, this will be useful to find out at what length of the bed it is actually getting dried out. Because if it gets delayed, the actual production gets delayed. Okay. Secondly, how much, depending on that, your coal consumption or fuel consumption will change. Okay. The quality of the product also changes. The other thing is, let's say you are using a very imported fuel. Okay. Coal is being, in fact, quality of coal in India is quite poor. So you generally these plants import coal from, say, for example, South Africa or Indonesia. Now you have to see whether how much all of that is getting utilized or how much of it is getting unutilized, because that actually determines the process economics. So you find out, and then it is also not uniform. As you will see here, these are at different bed heights, top to bottom. So the top layer gets consumed, but the bottom layer is actually there is almost like 20% gets unused. So then you have to see how to minimize this one if you want to really efficiently use the fuel that you are using this particular process. Similarly, I was talking about using some of this information for predicting quality parameters. So since we can predict the complete temperature profile inside the bed, now you put sensors anywhere and then track the temperature profile, let's say at different locations. Okay. Use this information, let's say for example how much time the material is seeing actually high temperatures, because high temperature phenomena that are happening inside the furnace have very strong influence on the pellet quality. So use this information along with other information and then predict the quality. So you have the raw actual data that is coming from the plant, and then predictions of this model, and use this for quality. Okay. So this for example, say one of the parameters like strength of these pellets. Okay. This is tested for example with several layers of data. So once you do this thing, then you can optimize it, or you want to control the quality by manipulating some of those parameters. Okay. And then ultimately you have to show the benefits also, because what is the purpose of doing all this? So then you have to actually show you are increasing the production through this optimization, or improving the quality, or reducing the energy consumption. Okay. So we actually implement this. For example, this was at SR Steel. They could actually improve the production by about 3%. This is for a company in Brazil, for example. It's known as Samarco. They could reduce fuel consumption. And the other important thing is that you could by doing this thing, these are all, let's say, direct immediate benefits. But there are other things that are also of importance. Many of these things, as I said, they use coal or coke. So there are environmental problems. How do you solve those things? So you could actually utilize this model, such models, for solving such problems. Other important problem, especially for India, I don't know how many of you know, for every ton of steel that is produced, they generate something like 400 kg of slimes, which are actually very rich in iron content, but they cannot be used for production of steel. So they are right now what I would say landfill in some locations. Every steel plant will have what are known as tailing dams. Now this is something like based on the production of steel that is being happening in India, something like 44 million tons of slimes are being produced. Now, this is one of the processes using which one could, there are processes being developed to utilize these slimes so that they can be used to produce steel. But some of this modeling activity could potentially reduce the trial and error, especially. Whatever I have discussed is about running plants, but one could utilize, because once you have figured out what are the kinetics, what are the heat transfer, what are the correct parameters, you could use such models for designing this process. Okay. So that's all I have. Before I close, I would like to thank Naveen for the invitation. I hope his decision to call me is justified, and I hope you find this useful. Thank you very much for your attention, and if you have any questions, I will be glad to answer.
So in your model, you're matching your experimental data. You showed one slide, but the temperature is going up to 300 degrees Celsius. Yeah. And then the later results, it showed that you are predicting temperature at 1400 degrees Celsius. So
see, this is the gas temperature.
Okay.
You are talking about this only, right?
Right.
Yeah. So this is the temperature of the gas which is coming out. This is not inside. So that is the temperature of the gas here.
Oh, this is the exhaust.
Not the temperature here. So what I am talking about, the temperature inside. So the temperature profile shown.
So then you are using this information to calculate temperature inside the reactor, is that?
No, this is used. This is not used. This is only used to validate the model online. So okay. This information is not used in the model. This is only to test the model. So given all these inputs, whatever is going in terms of physical properties, what is the temperature profile here, this is being predicted here. Okay, so this information is not used. That is to show that whatever is being predicted is matching with the actual data. So this is not used as an input to the model. And this is at the bottom of so what is, these temperatures are actually inside, these are bed temperatures, particle temperatures inside the furnace, inside the reactor rather. So here in this one. See, when the pelletization is started, then it will be like, say, it could be as small as microns to as big as millimeters. Okay, but then through balling that once when you start here, this will be about, say, micromillimeters. So it depends actually. In the case of pelletization, this will be all in microns. Okay. After this balling is done, you will get about, say, maximum size will be about, there will be screening actually. So the maximum size will be about, say, 18 mm, minimum may be, let's say, 8 mm or 9 mm. Whereas in the case of, let's say, centering, this particular feed size distribution itself will have very wide size distribution. It will have micron size particles as well as, say, 10 mm particles. Whereas this one here again, there will be a big distribution. So there will be particles as big as 10 mm, and then some of these fines will get layered. So you will have, let's say, 1 mm or something like that, 1 mm to 10 mm. Okay, I don't have the figure here, but it will change. It is the particles will be minimum, as I said. Here it will be microns to millimeters, whereas here it will be generally in say 1 to 10 mm. In some process, some process it may be 10 to 20 mm.
In great furnace, how did you decide your interface between different processes?
No, there is we don't define it. It will get predicted automatically. There is no, we don't detect it. It is based on how this. Yeah. So here
you are modeling it, right? From drying, combustion.
Right. So it depends on the actual conditions inside: temperature, composition, pressure. So based on that, it will get automatically.
All your equations are basically lump parameter, right?
No, they are not lumped.
So if this is a CFD model, you have done CFD model for it?
Yes, yes.
So then how you are tracking this interface?
No, when you say interface in the bed or in the particle?
No, in the
bed
flow.
Yeah, so you discredit this whole thing into, let's say 1 millimeter elements, okay, which is actually less than a particle size. Particle size will be about, say, something like mean size will be about 10, 12 mm. So every millimeter you track it, so automatically you will know where that.
From melting, solidification, and then you are going condensation.
Yes, yes. So it will be determined based on the conditions inside. So it will be computed automatically. You don't have to put any manual inputs.
Boundary conditions. Nothing.
No, you don't, because it will because these are all coupled. As I said, once you solve, you have to solve this in a 3 loops. Okay, so and you have to all the momentum, mass, and energy, all the 3 need to get conserved, right? So when you solve them together, it will evolve automatically. So like for example, this.
What kind of boundary condition you are imposing?
Boundary conditions will be imposed only based on what is known. I will show you just a minute. You know what is coming in here. Okay, so that will be the initial condition for this. Similarly, you don't know what is going on here. In fact, that is one of the problems. You know only what is going in here, because you can measure some temperatures in terms of that. And then you have pressures here. Okay, so only these are the given as boundary conditions. The rest is all whatever is happening inside. We have no idea of what is going on. So you use initial condition of the solids, and then this pressure drops, pressure at the top and pressure at the bottom, and basically the pressure drop, and whatever temperature information is available here. So that is used as the initial and boundary conditions. So all these, for example, these recycled streams, let's say for example this, in fact, missed some of those points. Like say, in addition to this, there are measurements here of temperatures here, etc. So once you predict it, so you will actually see whether the predicted temperature here is matching with the actual measured value. Okay. Yeah. So this is so you have to ensure that whatever the recycles, whatever is being measured is predicted correctly. Okay. So only initial conditions are with respect to solids as well as gases. I mean, basically in terms of temperatures and pressures, and of course any chemical composition that is known. Internally, you don't have to give any boundary conditions, because that has to evolve automatically based on the physics.
Porosity? How do you determine?
Porosity is actually there is okay.
That's basically your Argon equation, right?
No, Argon equation is to get the pressure drop. Oh, okay, I'm sorry. Porosity is actually predicted by another model. I didn't include that here. So porosity is predicted based on the size distribution of these pellets, and also because these are all wet pellets, wet granules. So the size distribution of not only the overall pellets, but also what is there in those pellets. That means the feed that is going inside, okay, and the moisture that is being used. Depending on the moisture, there will be deformation, okay, and also that is used to predict the void edge. Void edge is not. I'm sorry, I didn't. There is another block here actually, which will predict the wet void edge, which is then used as an input to the permeability model to predict using the Argon equation.
Any other question? If no, then let's thank the speaker once again.
Thank you.